Good morning, student. In last lecture, we have discussed about the mesh analysis and super mesh analysis. And in this lecture, we will discuss about the concept of mutual inductance and find the equivalent inductance in case of series connection and parallel connection. So before going to discussion about the uh, mutual inductance, first we are discussing about the problem that has been given into the last lecture. So question first is, see, find the value of I and B1 as shown in figure. Also calculate the value of resistance R. So see here in the question, 2 ohm resistance is parallel with 4 volt. So the voltage across this resistance is also the 4 volt. So current in this resistance is 4 divided by 2. So the current in this branch is 2 ampere. So this current 3 is dividing 2 is here, applying the KCL. So value of this current I is 1 ampere. So my first answer I is 1 ampere. Now see second answer, that is 2 and 1 is 3. So current in this branch is 3 ampere. So the value of this voltage V1 is 3 multiplied by 2. So the value of voltage becomes 6. But because we are entering from the negative terminal, so the value of V1 is minus 6 volt. Okay. Now third is, what is the value of resistance R? So first, is it possible to calculate the value of R? Because if we have three terms, two should be known to calculate the third value. So the current, this current is divided into this two branch. Okay. So now see 1 and 2. So we does not have information about this current and this current and about this resistance. Okay, we can calculate, we know about the voltage across this resistance 10 resistance R is 10 ohm, but we does not have information about the current, also the value of resistance R. So without knowing the value of this current, we cannot calculate this value of resistance. So in this equation or in this circuit, we cannot calculate the value of R. Okay, now we are moving on the second question. Find the equivalent resistance between terminal A and B. So see here, whenever we have to calculate the resistance, always short the voltage source. So this voltage source is short and this current source is the open circuit. Okay, so now see, this 2 and 3 ohm resistance is 5 ohm resistance, but it is shorted with this sorted path. So there is no use of this resistance 2 and 3, or this 5 ohm resistance is parallel with 0 ohm resistance. So value of resistance is 0. So only this 4 ohm resistance comes into the existence. So the value of this RAB resistance is the 4 ohm. Okay, so that is the answer of the second question. Now moving on the third. So see here, question third is saying, find, calculate the value of all the node current and node voltage as shown in figure. So see here, total number of unknown variable is I1, I2, I3, voltage VA, VB and VC, and next one is the V1. So see, this is my voltage V1 because this is the voltage of dependent source 3V1. So this V1 should be shown in the figure. By mistake we have forgotten. So now we are assuming this voltage is V1. Okay, so whenever a dependent source in the circuit, its voltage or current is shown into a resistance or in any other element. Okay, so this is my voltage dependent voltage source now and depend upon this voltage of this 4 ohm resistance. So total we have 7 unknown variables. So we have required total 7 equation. So one by one we are solving this. So see, between node A and C there is only a 10 volt source. So the value of voltage PA minus PC equal to the 10 volt. Second, between B and C node, there is only a voltage of 5 volt. So the value of BB minus BC is 5 volt. Third, between this node BA and the ground, there is only a voltage B1. We can say the 4 ohm resistance has the voltage B1. So the value of BA is equivalent to the minus of B1, and current is flowing in this branch, so that is also equal to the 4 into I2. So this is a wrong expression. Here is the term is PA equal to the 4 of I2, but the sign is just reversed as the current is entering, so this is the minus sign. So now equation BA equal to minus B1 with equivalent to minus of 4I2. Okay, and this is in this BB and the ground, there is only the source, and BB is having the positive terminal, so this is again BB equal to the plus of 3V1. Okay, remember BB equal to the plus of 3V1. Okay, now see, uh, next equation is I1 is the loop current of this branch, and that is the I2 of this branch current. So total current in this branch is I1 plus I2, that is opposite of 3 ampere. So I1 plus I2 equal to minus 3 ampere. So till now we have equation number 1, this equation 1, 2, 3, and with this minus 4 I to 4, 5 and 6. So total 7 variable, we have required one more equation. So see, we cannot apply the because this current source is in this loop and in this loop, so we cannot apply the KVL. So now we are applying the KVL in outer loop. So this point is suppose A, this point is B, this point is C, and this point is suppose D, and B1 is the voltage across this element. So this is negative sign and that is positive sign, and value of voltage is B1. So now starting from A point, plus sign, so that is 10 plus 10. Current, then resistance 7 with current I3, so this is plus 7 I3, and now we are getting the positive sign, so plus B1 equal to 0. So now we have total number of equations 7 unknown variable. By solving this one by one, we get all the value of node voltage and the loop current and the value of B1. Okay, now next we are moving on the concept of mutual inductance. So first, what is inductance and what is mutual inductance? So see, here we have shown two coil, A, that is one coil, L1 inductance, and this is my second coil. Okay, so whenever a current flow in a coil, there will always a flux is linked with the coil. Okay, and we can calculate the direction of flux using the right hand thumb rule. Okay, so if thumb is representing your direction of current, then your finger is always represent the direction of the flux. So suppose if the direction coil is same, if the direction of current in the coil is same, then the flux of one coil is support to the flux of the coil of the second coil. Okay, so this coil flux is also passed through the coil of the second coil. Then we can say these two coils are coupled with each other. Okay, if the flux of one coil is does not link with the other coil, then they are independent coil, and there is no effect of one coil on the inductance of the other coil. If the flux of one coil is linked with the flux of other coil, it always an induced voltage or EMF on the other coil, and we say that the flux are mutually linked with each other. So in the first case, the flux is supporting each other because direction of the current same, and in second case C, the direction of current is reverse. In this, in the first coil, current is entering to the from the terminal A, while from the second coil current is leaving to the uh, terminal A. So here the flux is opposing to the each other. Okay, now what the equation is related to the inductance. So the voltage V1 is linked with the L1 del I by del T. So first, this is not V1, this is V1T, because voltage is the function of time. For simplicity, we are just not showing the sign of the T, and this is I1T. So first V1 equal to L1 del I1 by del T. The voltage V2 is L2 del I2 by del T. If the mutual coupling between the coil is M and it is represented as K root of L1 and L2, K is known as the coupling coefficient. Okay, in frequency domain, this equation B1 L1 del by del T can be represented as, this is B1S equal to the L1S into I1. We are assuming that their initial condition are 0, and this is the equation L2S I1 into the frequency domain, and this is equivalent to the value of B2 into S. Okay, so that is the value of B1S and B2S. Okay. Now see voltage and current in case of coupling. Okay. So first, if the two coils are coupled with each other, we always convention as the dotted sign. Okay. If the current in the both the coil is entering with the same type of terminal. So see, in this case, current is entering from the dotted terminal, and from this current is entering from the dotted terminal. It means the flux is supporting to the each other. And if the current in the two coil is entering from the different terminal, it means flux is opposing to the each other. So one by one, we are studying what the effect on voltage and current. So see, if this coil L1 and L2, okay, inductance, this coil are mutually coupled with a mutually inductance M, then what is the value of equation V1 and V2? So first, this V1 has one equation of voltage due to the I1, and this is the sign as plus minus. So first equation is V1 equal to L1 del I1 by del T. This is due to the current I1. And due to the second current I2, because current is entering from the dotted terminal, it will induce a voltage, positive voltage at the dotted terminal, or it will support the voltage of the coil 1. So here we have shown with the positive sign. So the value of P1 is L1 del I1 by del T plus M del I2 by del T. Okay, same equation we can get from the coil 2. See, at the second coil, the first term is due to the current I2 is L2 del I2 by del T with the sign convention as plus minus. And due to this current I1, current is entering from the dotted terminal. So here is again a term as plus minus sign support this. So there is the plus sign. Mutual inductance is M, and that is del I1 by del T. Okay, these equation in time domain, if we want to represent this equation into the frequency domain, here this P1 is represented as P1 into S in frequency domain, while here is voltage is in time domain. So the equation is V1 equal to L1S I1 plus MS of I2, and V2 equal to L2S I2 plus MS of I. Okay. Now for the second case, see second case. In second case, current in the first coil is entering from the dotted terminal, while in second case, current is entering from the non-dotted terminal, because this is my dotted terminal here. So flux does not support each other. So see, what is the value of voltage V1? Due to the I1, this voltage is V1 equal to L1 del I1 by del T with sign plus and minus. And due to this current I2, what is the value of I2? So see, just wait, due to I1, this is plus and minus, and L1 del I1 by del T, and due to I2 is because current is entering from undotted terminal, so it will produce a positive voltage at the undotted terminal, and value is M del I2 by del T, and this term is reduce the effect of the reduce the strength of the voltage of coil L1. So here is the negative sign. So V1 is L1 del I1 by del T minus M del I2 by del T. Same for the V2. So for the V2, first term is V2 equal to L2 del I2 by del T, because current is entering at the undotted terminal. So due to I2, this is positive, and due to this negative. And due to the coil of I1, because current is entering from the dotted terminal, so it will produce a positive negative like this sign. So here is the term is minus M del I1 by del T. And here we have to represent the equation in frequency domain. Okay, these equation remain same. These equation remain same in third case, because in third case current are here current I1 is entering from the undotted terminal, while the second terminal current is entering from the dotted terminal. So equation remains same, because so whenever current is entering from the same terminal, the strength of the voltage will increase, and both the term will be added, uh, flux of the self coil and due to the mutually coupled coil. Okay, and if they are opposing each other, then the flux of the the EMF due to the mutually coupled coil is reduced from the self EMF. Okay, now moving. Now see here we have shown a problem. If connect a number of coil L1, L2 and L3 as in series, and suppose coupling between coil 1 and 2 M12, coil 2 and 3 is M23, and coil 3 is M31. Okay, and self inductance is L1, L2 and L3, and we have to calculate the value of equivalent inductance between these terminals. So see, what is the value of, so first there will always, because all are connecting to the series, so there will always a term as current is same. So first term is L1 del I by del T, L2 del I by del T, and third term is L3 del I by del T. The coil 1 and 2 current is entering from the dotted terminal, so the flux will support each other. So there is the third term is plus 2M12 del I by del T, because 2M12. Why 2? Because effect of L1 on L2 and effect due to L2 of L1. Current are same, so this is 2M12 del I by del 2. The current, the coil 2 and 3. In coil 2, current is entering from the positive terminal, while in coil 3 current is entering from the non-dotted terminal. So the flux is opposite each other. So this term is minus 2 M23 del I by del 3. And with the same case with the 1 and 3 coil, in coil 1 and 3, 1 is entering from the dotted terminal, while in coil 3 leaving the dotted terminal. So third term is minus 2M31 del I by del T. So the equivalent inductance of the coil is L1 plus L2 plus L3 minus of 2M12, minus, this is not the minus sign, this is plus of 2M12, and this is minus of 2M3, and this is minus of 2M3. Okay, clear? Next, now here we have shown a problem on the mutually coupled coil. There are the four coil L1, L2, L3 and L4 with suppose mutual inductance of each coil is 1 millihenry, and we are assuming that coil M12 mutually inductance of coil 1 with 2 M12 233141. Okay, all coil are related to mutually coupled with each other. M12, M13, M14, M23, M24, and M3, 4. So these all coil are related to each other. Suppose that is an 2 Henry. So what is equivalent inductance? So the individual inductance are added, L1 plus L2 plus L3. The coil L1 and L2 are opposing each other. So this is minus 2 M12. Coil 1 and 3 are supporting each other. So this is plus 2 M13. The coil 1 and 4 are opposing each other. So this is my 2M14. So first between 1 and 2, 1 and 3 and 1 and 4. This is M12, M3 and M14. Now 2 and 3, 2 and 3 are opposing each other because current in this from the dotted terminal, undotted terminal, and here from the dotted terminal. So this is minus 2 M23 and uh, 2 and 3, and 2 and 4, between 2 and 4 current is entering from the undotted terminal. So this is plus 2 M24, and between 3 and 4 coil they are opposing each other. So this is minus 2 M of 3. So total inductance of the coil is 4L minus 4M because L1, L2, L3 and L4 are equivalent to the L of 1 millihenry and all M are equivalent to. So this is putting the value of L as 1 millihenry. This becomes the equivalent to minus 4 millihenry. Minus sign is just indicating is that the flux is opposing to the current flow. Okay. Now moving to the next. Now suppose coil are connect in parallel. Okay. Now here we have shown the coil L1 and L2 are connecting to the parallel. Calculate the equivalent inductance between the coil. What is the equivalent inductance between the coil? So see, suppose this voltage is V. Okay. So now first is V equal to in frequency domain. This is SL1 I1. Now this current I is dividing two branches. So current is suppose in this branch is I1. So current in this branch is I minus I1. So first equation is SL1 I1. And due to the coupling, because flux are supporting each other, we have assumed the current from the dotted terminal. So this is MSI minus I1. So this is due to the L2 on effect on L1. Now second B equal to on the second term, this is SL2 I minus I1, and due to the mutual coupling, this is MS of I1. Okay, because these both are the voltage be equivalent these two terms. Okay, first and second, and the get the value of I1 in the term of I is I1 equal to I L2 minus M upon L1 plus L2 minus 2M. Now put this value of I1 into the equation number 1 because inductance be equal to LdI by dt. So we have to remove the variable I1. So when we put the value of I1 in equation 1, so equation 1 can be rewrite as L1 minus M into I1 plus Ms of I. Now in this equation we are putting the value of I1. So my equation become B as L1 minus M, and that is the value of I1 is L2 minus M upon L1 plus L2 minus 2M into I plus Ms into I. So this is B. What is total equivalent impedance? B equal to L equivalent, L equivalent, and into S into I. Okay, S into I. So L equivalent of the circuit become just leave all the term, multiply this L1 L2 minus ML2 minus ML1 minus M square divided by this term plus M. Okay, so rewrite this equation. Now L equivalent of the certificate become L1 L2 minus M square upon L1 plus L2 minus 2M. Okay, see, always check the unit of your question. Okay, here is L1 L2, that is Henry square. So here is always come as M square. Okay, so the question should, your expression should be correct by the unit wise. So there is the term like this L1 L2 minus 2M not possible because here is the unit is Henry square. So this also has the unit of Henry square. So in unit wise, the numerator has the unit Henry square, but denominator has the unit Henry. So this is Henry square divided by the Henry square. So this is Henry. Okay. So in case of series, when the coils support the flux of each other, the equivalent inductance is L1 L2 minus M square divided by L1 plus L2 minus 2M. If this second case, if this flux is opposed, suppose this is not the sign is here, if sign is given is here, what is the equivalent inductance? In this case, numerator becomes same, only the denominator is represented by plus sign, plus 2. Equivalent inductance will be decreased compared to the first case. Okay, now see, next, like numerical example for the practice section. Here, calculate the equivalent inductance in this first case, L1, L2, and L3. Okay, is given as 1 Henry, 2 Henry, 3 Henry, and coupling between them is given as 1, 2, 3, 2, 3, and 3, 1 as 2, 1, 1. So find the equivalent inductance between these two terminals. This is the first question. And in second case, calculate the inductance, equivalent inductance in the case of parallel case. This is my second case. Third is very important question. You have to calculate the value of I. Okay. How can you solve this I? Taking with minimum effort. So just try this problem. Okay. Before the next lecture. Okay. So today we will stop, and in next lecture we will start the network theorem, and in next lecture we will discuss about the Thevenin, Norton, and maximum power transfer theorem. All three theorems are related to the each other, because if you know about the Thevenin, then there is nothing in Norton. If you know about the Thevenin Norton, there is nothing into the maximum power transfer theorem. There is a lot of question into the competitive exam in GATE, PSU, or another related to the Thevenin, Norton, and maximum power theorem. So we will discuss all three theorems for the DC as well as AC, and the number of numerical based on this theorem. Clear? Thank you very much.